Okay, let's take a look. Let's start with the interface. Equipments, we can maybe have price, and also we can have name, whatever you need. Remember, only method signature, right? That's equipment. On the other end, we also got this composite generic class, which we got children, we got add, and you can feel free to add more methods there, maybe remove, maybe add a particular index, and etc. Right? So these two classes are what we start with. Let's see at the intermediate level what we have. We can have another class called base equipments. Okay? For the base equipment, it simply implements the equipments class. And it has nothing to do with the composite, right? Only base. Okay? And what do we have? Well, in this case, I just got some attributes over here, and then I got some constructor, and then just accessor. Very basic. You guys will work out what kind of common methods or attribute you want all the base equipment or base expression to share in your project. You guys will figure that out. Okay? And for this one here, yeah, just reusing the constructor. Okay? That one's not exciting. Let's now take a look at the composite equipments. We only look at the design diagram earlier, but let's now look a little bit more deeper into the code. And let me just give you some look ahead. You will see that I got some comments over here about dynamic binding. That's something you heard back in 2013 and 2011. And I'm going to go over the code very quickly, and then I hope somebody can tell me why dynamic binding will be exercised over here. We'll get there. For composite equipments, you will extend and also implements, multiple inheritance. That's our workaround. And also, every equipment has a name, and also constructor, that's easy, and also the name itself, just return the name. The price here is interesting. Remember, I talked about uniform access principle. Let me just make it even more explicit this time. At the equipment level over here, you can see the price method that every equipment should really implement is called uniform access. So now we got two cases. Case number one, you can see the price for the base equipments will simply return the attributes. There's no computation involved. Whatever price you assign each base equipment, like a card, drive, and etc., that just return it. That's access one. And what about access 2? It is over here. In the case of the composite equipments, how do you figure out? Because composite equipment simply got some children. Each child can be themselves also composite. So it's a tree structure you have to traverse recursively. And over here, let's see. You got a result, and also you want to go over the child one by one. And this, by the way, this is the for each loop. If you have seen that before, you can use it. Or you can use the more traditional for loop, with a loop counter. That's fine too. We'll simply go over the children list one by one. And then every time, we're just going to increment the result by child.price. All right? And again, this one here is also making use of the uniform access, meaning that the single access is going to cover recursive and base cases. And can anybody explain to me why dynamic binding can be exercised in this particular method call? Dynamic binding. Do you guys remember what dynamic binding is? Robbie? Because the child, because the dynamic type itself can either be a base or a composite. Yeah, sure. As we'll see some concrete example how to set this up. Okay, the child. Yes. Now, Robbie, I see what you mean. I didn't notice that. The child over here, the context objects. This, its dynamic type can be either the base equipments or the composite equipments. Base or composite. If it happens to be base, it will just return price like attributes. If it happens to be composite for the dynamic type of child, in that case, you're going to involve the recursive calculation of this particular loop until you actually reach some base case and terminates. All right. I'm going to give you guys some maybe hand waving a bit using the diagram, but there's something, hopefully it's not too heavy. Right? So that's about the code for every class that's involved in this composite pattern. Are you guys okay? Okay. Hopefully not confused, right? Okay. That's about all the classes I just went over. And once we dynamic binding also explained, let's now try to trace this test case very quickly, and then we are done with the composite. So we can move on to visitor. Okay. Here, why don't you guys stare at this code for just 1 minute? Two things I want you to imagine in your mind. Number one, what kind of tree is being built at the runtime? Number two, when I call this method here cabinet.price, how exactly is it going to calculate? Okay. Okay, give you 30 seconds more, and then we should really go a little bit deeper into this. Okay. All right, let's now take a look. You might be thinking, well, since the only number that are being mentioned here is 200 and 500, just add them up, and then you got 700. True for this example, but I might ask you in a different way in the quiz or the test. You want to make sure you know how to build that particular tree structure. Okay, we'll see. Let's take a look. All right. So this is the test you just read. Okay. I'll try to use a cost stack to show a little bit. I'll try not to stay here for too long. Otherwise, you can easily get bored. But it's not too difficult to trace. Okay, we'll try. And that's the code for base equipments, which we just went through. That's the composite equipments. And if you remember uniform axis, you will see price over here, base case, just return the attributes, and also price over here, which is going to involve some complicated for loop computation. Right? So we got two cases here. And let's now go over the code very quickly. Over here, just declare the attributes. Right? So we got different variables. We got cabinets, we got chassis, we got bus, we got drive, we got cart. Okay? And we're going to create all these objects. Right? So let's assume we have done that. For example, the car over here, you can see, let's try this one. So the car here, it has a car, and the price is 200. Let me fill out the 200. And also for the disk drive, it's 500. And all the other objects are just like that. Okay? You can, for example, let's say for the cabinets, it has a list of children. I'm cheating a little bit here because eventually it's only going to get only one child. That's why I draw that already. But of course, it starts with empty. Okay? And let's see this part over here. That's how you build a tree. That's the easy part. And we're going to see how to calculate recursively after that. All right, let's try that quickly. So for the bus, add card. So that means for the bus over here, it's going to add as a first child just the card. Right, there's a link over here. And then also we got the chassis. Chassis over here, got bus and drive. The chassis is over here. So the first child will be a bus. The second child will be a drive. Right? Almost we're going bottom up, basically. Okay? And finally, we got the cabinet. And for the cabinets, the first child will just be a chassis. That's the tree. Here, I'm basically give you the code and ask you to visualize. What I can ask you to do instead, give you somehow the visualization here, or the visualization like this, and then you want to write a Java code to build that tree. You should know both ways. Okay? All right, a final thing for us to do is to see how to trace this line of code. This one, cabinet.price. Of course, if you say drive.price, 500, If you say car, the price, 200. If you say, for example, bus, the price, not surprisingly, it's only going to contain 200, right? It's going to be 200 as well. What about cabinets, the price, right? The answer should be 500 plus 200, but we want to see a little bit into how the recursion works. I think that's really important. All right, let's try. So that's what we will do. So let me start with cabinet price. And cabinet itself is a composite. So we're going to execute the price over here. Okay? So that means we're going to have some result, and we're going to here to do a for loop. Right? The for loop is going to go over all the child for this cabinet. Okay? Oh, by the way, cabinet is here. Okay? Just in case you didn't see that. And how many iterations are we going to have? Just one. Right? Agree? Just one iteration. And then the result somehow should be updated by the child.price. And this will be the child. So that means the cabinet's price should be equal to the price for its first child. All right? Let me just put a stack over here. I'll try to do a little bit. Okay? So we start with cabinet.price. And to really compute it, we have to say cabinets. Let me use a different color. Dot children at index 0. And then that one there, dot price. Agree? Okay. And how do we compute this particular chassis, its price? We have to, well, because we know this cabinet dot children at index 0 dynamic type is chassis. Again, it's composite, so we got to call this version again. So this, when we execute this, let me only go up to here. But what's going to happen here? So when we say this, it has 1 and 2 children. So that means if you try to execute this, you're going to have 2 iterations, right? That one is going to involve chassis, the children, and then index 0, which will compute the price for this one here. And then that one dot price. We're going to do this one first before we can go to the next one, right? And how is this one going to be computed? Well, that one there, too bad. It's just another composite. Agree? So let me go a little bit quicker. In order to calculate the price for this one here, we call the price method on this again, which is going to involve the loop again. And that one there is going to compute the first child, which will give us 200. Okay? So eventually, this part over here is going to give us 200. So that one there is only the first child for the chassis. So what we're going to do is just another one here. We're going to compute the second child of chassis. So, and that will be index 1, the price. That one there, we're lucky. It's just the base case, which will give us 500. And by the way, when you call this price here, it's going to call this version, which will give you just the attribute. So that'll be 500. So eventually, you're just going to add up these two numbers, right? And in your project, I don't think you're actually going to maybe to trace your code like this for the complicated tree. But just in case, if you got any bug in your code about recursion, you may just want to start with some very, very simple test case with some very simple tree and try the method you actually you believe has some error and try to see if you can reproduce some tracing here. That might help for debugging. Okay. All right. All right, any question about composite? It's a very quick review or introduction to the pattern. But you have to make sure you understand the different design attempts and also polymorphism, dynamic binding, and also how things work at the runtime, right? Anything is possible in the quiz or in the exam. Any more questions? Well, you haven't got questions so far. Go ahead.
Why is your video card negative token?
Just whatever it is.
What's a video card?
Hmm?
It says video card.
You know, I just copied that from some earlier slide. May not make sense. Sure. Yeah. Just some string description. That could be wrong. Okay. All right. I presume everybody's okay. All right. Let's now move on to the visitor design pattern, which depends on the composite. And this slide here simply just summarizes also things that we discussed already. So polymorphism, dynamic binding, the uniform access principle, and also whenever you say equipments.price, depending on the dynamic type, you might call different equipments, either base or recursive. All right? All right, visitor. And for the visitor, the main thing would be at the end, when we talk about the double dispatch. That's something, if you haven't learned about visitor before, that's something you definitely should know when you talk about visitor. And we're going to see, how we can think about visitor is assuming that the system you're trying to apply the visitor to is a recursive system. If your system is simply not recursive, there's no point of applying visitor. All right? That's why Antler 4 actually support visitor, because abstract syntax tree itself is always recursive. And we're going to see some alternative design, and then we're going to learn about several design principles. We're going to see cohesion, single choice, and also open-close principle, right? So these are the different principles you might have learned in 3311. You have taken the course, or something you will learn later. And then we're going to see visitor design pattern. And we're going to see how you can implement and test the visitor design pattern. Okay. And let's assume we already got this composite structure. I'm omitting some detail over here. I simply put composite expression directly. There should be another inheritance relationship over here about inheriting from composite. I'm just omitting it. But when we present a final design for the visitor, you will see everything. But for now, just easier for discussion. Okay? And that's basically something you had to do for the practice test and also for your tutorial, during the reading week. Let's say we want to design some structure or syntax, abstract syntax for the language. Either you got integer constant, 341, 2, or you got just addition. Right? You can think about extension for later as well. That's okay. Okay, let's say that's what we have. And just notice that for composite expression, we got either left or right, assuming there's a binary operation. And here is the question, which will be very relevant to your project. Let's say, given the abstract syntax tree, we actually want to support various operations. I'm just giving you some example. It could be pretty printing. You may want to pretty print maybe the tree in prefix notation, postfix notation, or type check. Of course, there might be other operations you could potentially support. Maybe you want to generate C code or generate Python code from your tree. And the question is, if we try a very naive solution, let's see this. So what we have is, we have this composite tree structure, which we just saw, right? We see how it can be traced. And these are the various operations. I'm going to propose just one possible design, which will work for sure, but is it really the ideal design? Let's give it a try. Since we want to support 1, 2, 3, 4, we want to support 4 operations. Okay? Let me just name them so easier for me to write. Operation number 1, operation number 2, operation number 3, operation number 4. Okay? One obvious design would be, why don't I simply declare all these operations at the expression level, unimplemented? That's for interface. So I can declare operation 1, operation 1, operation 2, operation 3, operation 4, unimplemented. So this was, the nice thing about this is syntactically, Java is going to force all the descendant classes of expression, either base or composite, to always implement operation 1, 2, 3, 4. Agree? Okay, let me write it down so you can see more explicitly. And for the constant, I'm going to implement operation 1, operation 2, operation 3, operation 4 in one way. For example, if you want to evaluate the constant, just return the value. evaluation is pretty easy. And you also need to implement at the composite side for addition. You gotta do operation 1, operation 2, operation 3, operation 4. And obviously, for operation 1, which is evaluates, for the composite, it's gonna be harder because you have to make sure the left-hand side is evaluated first, combined with the evaluation result for the right-hand side. Agree? It's just more complicated. That's why I use different color between the two. This is one valid design, which means it will work programmatically. But it violates certain design principles, which I'll show you, but do you guys see intuitively what can go wrong or what may not be so nice for this design? You can think about, for example, I'll give you a little bit hints. What if a new operation is needed? That's one hint, one way to think about. Number 2, what is the very purpose of a class? So these are the two hints. Somehow correspond to the two design principles I want to talk about. Any thoughts you guys want to share? What about the first one? If I want to add a new operation, maybe I want to generate some assembly code, let's say, operation number 4. In that way, what should I do to all the classes? Yeah, William. Yeah, you definitely have to, number 1, declare operation number 4 here, and then implement it here, implement it here. Here we're talking about a very small inheritance hierarchy. What if the inheritance hierarchy has many classes over there? In which case, you will need to touch many, many places in your system. So whenever a change is needed, there is a design principle called a single choice principle. You may just want to touch as few places as possible. Okay, that's the number 1. And I'll go over the principle in definition. And number 2, a class, right? So there is a notion called Superman class. Have you guys heard about that notion before? Superman class. You might just be able to guess what that really means. What does it really mean when I call a class a Superman class? Well, that means you're having a class that is capable of doing everything you want to do. That's what we intend to do, I would say. You can think about the Superman class is really the extreme, opposite to modularity. Whenever we talk about modularity, that simply means you want to have as many modules as you can, which will collaborate with each other in your project. Superman class means you want to have just a single class where you put all the methods, no matter how related they are, in a single class. Programmatically, this will work, this will also work. But from a design point of view, this should not be the case. That will make the design, make the maintainability just so much worse to achieve. All right? That's just a kind of design principle you want to also consider when you do the project. All right? Let's now go over the 2 design principles here. Okay? So this is one design attempt which will violate 2 design principles. Right? Let's now go over them. One is about cohesion. You don't really want to have a Superman class. So here one can argue the evaluate, print, and also type check, yes, they are like an operation to be applied to the tree. That's true. At the same time, are they really similar operation themselves? Not really. The way you do evaluate has a very different nature of if you just want to print or you just want to type check. You shouldn't really put different kind of operation in a single class. Right? That's one way to argue. Right? So cohesion, that's the definition. You should only put relevant features in the class. That's something you guys can judge. If you got, for example, more than a certain number of methods in your class for handling maybe the programming language or the testing language, it's a warning. You may just want to put them into separate classes that has either inheritance or client-supplier relationship between them, right? That's something you will have to judge. Right? I can only give you just the principle. And single choice principle, which I also mentioned. The intuitive way to understand it would be you don't want to have duplicates, right? Or whenever you want to make a change, you should just focus on as few places as possible. So the definition goes like this. And we have to review this single choice principle again once we see the visitor pattern. So when a change is needed, and you just want to change either a single place, if possible, or a minimum number of places. Of course, you want to justify why the multiple places you have to change is really the minimum. It's kind of up to your judgment, right? So that's why I include. That's another possibility, okay? And if you really violate, very often it's because you got redundancies, right? You may, for example, one way to get rid of the redundancy is you can factor out all the duplicates into a single helper method and then call the helper method instead, right? Like we have a generic class called composite that can be instantiated by multiple packages in the project, right? Similar idea, right? A little bit abstract here, but we'll try to apply these principles as much as we can. All right. Are we okay so far about the principle here? All right, so this slide here is just trying to argue why this design over here is not ideal with respect to a single choice principle and also cohesion, right? All the points have been just discussed, okay? And of course, maybe more to your interest, if I give you some certain design, let's say in the quiz or in the test, I would say, now consider this particular design for the following purpose. Now, you want to justify if the design is suitable with respect to maybe cohesion or maybe to single choice principle, right? That's something you will need to know how to justify, all right? Okay, one more principle for today before we talk about the visitor. It's called the open-close principle. It sounds a bit contradictory, right? How can something be open and closed? Basically, it means that for the system or for your package, or I mean for the model package, certain parts ought to be open. Certain parts ought to be closed. Being open means they are unstable. They might just be subject to changes. Being closed means they are very stable. Once they are initially developed, you shouldn't really touch them often. Okay, that's open-close principle. Okay, it's kind of up to your judgment about which part of your system should be open and which part should be closed. But we're going to use the visitor pattern to explain. Let's go over definition quickly. So your classes, features, methods should be open for extension and also closed for modification. But just remember, open means that's the part being unstable. That's why they're open. And closed means they're rather stable. They shouldn't be touched often. Okay? And so here, let's see here. We want to talk about, we're getting very close to the visitor pattern. For our expression language, you need a composite. So there are basically two parts we want to consider. Let me show to you, okay? We got two categories of stuff. One is about the structure, the syntax. You can think about this part here is what's the antler 4 can generate for you, the syntactic structure, okay? The structure part. We got another part, which is about the operation we'd like to support for on the tree. Could be evaluate, pretty print, or type check, right? As many as you like, okay? So we got these two. So our system basically contains these two parts. And now, if we want to apply open-close principle, we got two possibilities, right? You wouldn't want to keep the entire system open. You wouldn't want to keep the entire system closed either. So either open-close or close-open, basically. Right? If you look at this table here, right, we're going to talk about these two possibilities quickly. Possibility number one would be, we would say the structure part over here should be open. What does it really mean? That means you're quite flexible of adding new language features. That's what it means to be open. And what does it really mean to be closed? That means once you implement the initial list of initial list of operations, you don't really expect new operation to be added. That's what it means to be closed. Okay, so you can see one possibility is open for the structure and closed for the operation. All right. So open here means the syntax of expression subject to changes. And here, when we talk about the operation being closed, so that means the list of supported operations is pretty much fixed once you develop them. Right? So that means you got to have a very clear idea what you want in the beginning. Okay? That's alternative number one. Okay? So here we haven't talked about anything technical just yet. I just want you to know, for the open-close principle, deciding which part should be open, which part should be closed is completely up to you. But you ought to know what's the consequence if you decide one part should be open, the other one should be closed. That's the main point. Okay? And let's now talk about the second possibility, right? The same system here. So we still got structure, we still got operations over here. And what does it really mean? Alternative number two. We kind of flip, right? So now the structure over here is closed, and the operations over here is open. You can kind of guess what that really means, right? Structure being closed means we don't really expect new syntax to be added. Okay? The close over here, no new syntax. On the other hand, for the open here, you can keep adding new operations. And alternative one or alternative two, you can only decide to be one, but not both. And later on, we want to know, in order for your system to be applicable for a visitor, one of the alternatives should be the case. Okay? That's something we'll see. Okay? And I think the next one will be just the final architecture for visitor pattern. Why don't we take a 2-minute break by taking attendance? And then we'll go to the visitor. Okay. Okay. All right, let's see. View the course online. Yeah, bear with me, it's a bit slow. Settings, attendance, don't require, allowed, and save. Okay, start a class. Okay, you can check in. All right, no issue, right? All right, can I stop here? All right. Boom. All right, thank you. Yeah, let's take maybe until 3:32, about 2 minutes, and then we'll start a visitor. We should be able to at least finish the double dispatch today. And then there might be some minor stuff we got to finish on Tuesday after the quiz, but it should be enough. Okay, 1 minute. Okay, let's now resume. So we want to go over, first of all, before we dive into code, we want to look at architecture diagram for the visitor. And I would suggest you can simply just go to the lecture site. I already uploaded the diagram. I'll show you which diagram you should really open, okay, if you got your computer with you. Go to lecture 13. You will see visitor architecture. That'll be larger for you to see. But of course, you can zoom in and zoom out. Okay, so that'll be the one. And to really see the best way to understand the visitor, well, actually, we got a very nice small language to see. So that's why it's reasonably okay to manage. But I'll show you the rule. Okay, and of course, you might think this is not exactly the same as what's being generated by the Antler 4. I agree, not exactly the same, but the general idea is still consistent. Maybe I'll just highlight at the end. Okay, let's now take a look. Okay, I assume you can find the diagram yourself. Okay, so let's see here. There are two packages we want to focus on. Okay, one would be the structure. Remember we talked about open-close principle before the break. One will be structure, the other one will be operation. Okay, so we got structure will be one package, which is about the syntax of the AST. We got also operation, and you can see in the operation we got a visitor over here. Okay, and then one thing to note, in the structure part, you can see we basically got the same classes. We got expression, we got constant, addition, the same as before. The only difference is we have added at the top interface level a method called accept. That's the standard term to use for the visitor. Okay, so in the structure part, we got some accept method that every class over here should implement, number one. Number two, on the operations package, we got a visitor interface as well. And under the visitor, the number of methods you want to have, which will force all the descending classes to implement, the number of them depends on how many leaves there are in the structure. Okay, I'll be more precise. Okay. Let's see, I'll talk about this one a little bit later. Let's take a look at the visitor, okay? First of all, you can see visitor here. In Java, the naming convention will be we start with visit, and also visit. Visit constant, visit addition, visit subtraction. Not surprisingly, we got constant, addition, and subtraction. You might see some variance sometimes. For example, you can see addition and subtraction, they got some common intermediate superclass called composite expression. In some cases, you might also see visit composite expression. That's fine too, right? That's also still being consistent. I'll put it here. I'm talking about the minimalistic visitor. Optional. You might have visit composite expression. That's also possible. Okay. And then let's see what the parameter types are for each of the visitor method. Here, if I say visit constant, constant. Visit addition, addition. Visit subtraction, subtraction. Not surprising, right? And then how many descendant or subclasses you want to have under the visitor depends on how many operations you want to have. You got evaluator, you got pretty printer, you got type checker in this case. Let's brainstorm a little bit. What about for your projects? What kind of operation do you want to apply? Anybody? We can brainstorm. Do you want me to do some, what? Type check definitely applies, right? You may want to do some type checking on the input language. What else? What kind of operation can you do on the AST? Right? You guys want to think about it. I don't want to give you too explicit hints. Right? Think about it. think about in your projects what kind of operation you want to have. Whatever you come up with, they're going to become some visitor descendant class. And then in that particular class for the operation, you want to make sure you support the visit method for every language structure. That's the idea. Okay? So this is just the architecture. We're going to see exactly how to use it. Okay? I'll get to that very soon. And this part over here is just the composite. Right? You can think about this is just the composite. And then you can see here, this is the main method that we have added in order to support the visitor pattern. This is to say, for any expression, either base or recursive, I can say, let's say expression E. Think about what the consequence is if I try to do this. If I declare it, oh, you know what? Let me put it here. The consequence of this is this. If I say expression E, which will be of certain dynamic type, which can be base or recursive. And if I say E.accept, this accept method over here, what I expect to pass over here would be some visitor. Right? And how many possibility are the dynamic types over here? Can be here, can be here, can be here. So that means if I'm given a particular expression, I can simply say E.accept always, depending on what I want to do. If I want to pretty print expression E, I can pass a pretty printer. If I want to do type check on E, I will pass a type checker, and etc. Right? That's what I can read, at least from the architecture over here. Of course, we're going to see more concrete example. All right? Do you guys have any questions just about the architecture here? I think it's reasonably complicated, right? But I think that's kind of the minimum example we can use to illustrate, right? And one thing to say before I show you some example code. You can see there's a client-supplier relationship over here because you can see under the expression at the top level, the parameter type is visitor V. So that's how we link between the expression and also the visitor. Right? That's how we link it. Just remember. So this arrow over here is really important. So these two packages are not really unrelated. Okay. Any question about this before I move on to maybe a little bit concrete code? Okay. Let's now take a quick look. I don't want to do tracing just yet. At least we can see how we can use it. Okay. Let's say we got composite expression we got expression C1 and C2, which will be constant. That's why I call C. Also, we got some visitor. And notice that, right? This will be reviewing what you learned in 2030, right? Visitor over here is the static type of the visitor. And the static type I'm using here happen to be the top level. That means dynamically, I can bind V to either evaluator or pretty printer or type checker, depending on how I set it up. All right? Hopefully you understand what I mean. Right? And let's see how we can set it up. So C1 will be a constant, just with value 1. C2 will be constant 2. And also add will just be C1 and C2. Basically, we are trying to reproduce 1 plus 2. Some simple example. But it's a tree, of course. And once we have constructed the composite add, you can see new addition. We pass the left subtree and right subtree. They happen to be just leaves themselves directly, which is OK. And then here you can see this evaluator is the dynamic type of the visitor. Right? Doesn't need to be evaluator. If you want to do type checking, you can just say new type checker. Okay? So this will be dynamic type. Dynamic type. And the most critical line, which I briefly mentioned, is this line here. Okay, this line. I say add dot accept v. What does that mean conceptually? This is the expression I would like to handle. Normally, it should really refer to the root of the expression tree you want to handle. Or it could be that while you're doing the recursive call, it could be the intermediate subtree you have to handle. That's also possible. But normally you start with the root. Okay, let me just make a note over here. The root of AST to start processing. All right, and then after this, and we're going to trace this line very carefully. It's going to trigger some runtime phenomenon called double dispatch. Whenever people talk about visitor pattern, it's about double dispatch. All right, we'll talk about it, at least for today. Okay, I got 8 minutes. I'll try to do a little bit hand waving, at least you have some idea. We might have to do some detailed tracing in the beginning of Tuesday, but let's do as much as possible. After I have said this, right? This line here is going to involve many things. It's going to involve the visitor v, which happen to be an evaluator, going over the tree structure of this context object, which is add. And then once the processing is finished, the visitor itself stores the result of the processing. That's why you see me say evaluator.result. And I have a very important question for you guys. Very important. Okay? I'll post the question here. You can see I'm doing some anonymous casting, right? I'm pretty sure you know how to do it. Okay? The question is this. Can I write v dot result without the casting? So instead of casting v to evaluator and then dot result, that one works. Can I do v dot result? If you don't believe you can do it, can you tell me from the diagram, how did you figure that you cannot do it? Anybody? Anybody besides William? I'll be happy to point to him, but you want to try? Yeah. Okay, you try first, please. Yeah, that's pretty much it. Very good. And let me just be a little bit more polished on the answer. The complete answer should be, the v over here was declared to be a static type visitor. The static type of v is visitor. And if you look at the visitor, do we have the result method over here? We don't. Result is only a subclass specific method that's defined over here. So that's why we cannot do it. So the visitor pattern only tells you the minimum methods you have to support, like a visit. If you want to add any operation-specific methods, either for the evaluator, for 3D printer, or other things, you have to add those extra methods at this level. You wouldn't add them over here. All right? Okay, let me just finish the answer here, which does not support result. All right, so that's a little bit about how you can use the visitor pattern. Okay, just basically expression.accept some visitor. And this part would be the most important page. I only got about 5 minutes. I'll see what I can do. Right? I'll hand wave a little bit to you guys. Okay? Let me just talk. I'll also make this page available. You guys can do a little bit of mental exercise. Double dispatch is a little bit tricky. Okay? What we want to do is like this. We want to say expression dot accept some visitor. The essence of double dispatch goes like this. Add over here is a reference type. That one has a dynamic type. V here is just another reference type, also has a dynamic type. Agree? Every reference type has a dynamic type, every reference variable. The expression has some dynamic type. which could be, for example, constant, or it could be addition. And the visitor over here also has a dynamic type, which could be, for example, evaluator, pretty printer, or type checker, right? So now, depending on the combination of the dynamic types, we might end up calling different accept or different visit method. That's really the essence for double dispatch, okay? So what I would like to do now is to help you a little bit as follows. Let's go over the definition quickly, just in 3 minutes, and I'll give you some hints about what kind of exercise you can do, just to think about double dispatch even before I talk about it. So for the expression part, we got constant, which implements expression. And for the accept, the definition is incredibly easy, okay? The visitor v is the arguments, the parameter. We simply say v dot, since we know we are currently in constant, so we simply say visit constant. And the visit constant method, for example, in the visitor pattern, is expecting some constant objects over here. And what we are passing over here is, since now we are in the context of constant, so why don't we just give this the current objects? So this over here is normally the tricky part to get right. Similarly, when we talk about, let's say, addition, which is just the composite expression, we also got accept to implements, but now we say visit addition, corresponding to the addition here. And then we can just pass this, the current objects. The definition for the accept for each expression class is very standard. There's no variance, really. Okay, very quickly, let's take a look at the visitor. I got 2 minutes. Visitor here, we got visit constant, visit addition, visit subtraction. Let's take a look at evaluator, just one of the descending classes. We got some result, and we want to create a visitor. That's fine. Let's take a look at this one here, this one. Okay, I'm going to dive deeper into this next time, but take a look at over here. Think about what's happening here. Visit addition is going to somehow visit the parameter addition. We know that the E over here, which is addition, can be arbitrarily complicated. In general, it could be that E is pointing to some plus, and that one there has 2 arbitrarily complicated subtree. Agree? The left and the right. So the idea about over here, what we have is to say, in order to visit this addition, we have to visit the left subtree first, get a result, and then visit the right subtree, get a result, combine them, so we can set the overall visit result for this plus. Okay? That's kind of the idea. And I don't think you really need to understand double dispatch for the Saturday's test, so I think it's okay for us to talk about double dispatch in detail, maybe on Tuesday. And for Saturday, yeah, just make sure you come before 2 p.m. Me and the TA, we will be there about 1:45 in the person lab. We'll set up the room very quickly, and then once we think you're ready, you can come in. All right? Guys, do you have any question? And one more reminder. You ought to submit your team.txt file to the project init folder. If you haven't, please do so. All right, I'll see you guys on Saturday. About the visitor pattern. Let me remind you very quickly about the architecture. Right? You can see that's the architecture for the visitor. Right? Let me do a recap very quickly. This part here should be no surprise to you. What will be the connection to your Antler 4 project? We definitely got some visitor-based interface that's generated based on your grammar. You can do the hash sign, some name, right? So you can get a corresponding visit method. That's something you did. And also you can create as many descendant classes for the visitor as you like Antler to program, Antler to expression, right? That's the descendant classes we're talking about. And the only part that Antler 4 cannot really generate for you is about the accept method. So this is something we will talk about in the theory in the class, but for you to really 100% exercise the visitor pattern, you may just want to say, for the hierarchy of my programming or testing language, I'm going to define this accept method at the top so that I will be actually implementing the accept method for every descendant classes. Right? That's something I want to emphasize. So for this method here, this will be up to you to actually define, right? Defined by you. All right, that's something you want to pay attention to. And then we are going to talk about how to implement each accept. We actually spoke about it already. It's actually going to be very straightforward for each one of them. You just want to make sure you you call the corresponding visit method. For example, in the case of the constant class, the accept method is going to call v.visit constant. In the case of the addition, the accept method is going to be implemented by v.visit addition, and etc. Right? That's how you use it, how you implement it. And the final second last bit is to talk about how the double dispatch is going to work at the runtime. That'll be the second last bit. Let's talk about it. Okay, so I'm just going to duplicate this page over here, which I forgot to do. Just bear with me. And then I'm going to start from here for today. Okay, let's now talk about just this particular line. Let's say we have already created this add variable. And add is simply pointing to the root of some expression tree, a simple tree, of course. And the tree has simply a left and also a right. In general, it can be arbitrarily complicated. The left subtree can be itself some expression. And the right subtree can also be itself some expression tree, of course. But in this case, just simple, so we can trace. All right? And also, we got some evaluator objects over here. And the source code has already been made available to you. There will be certain parts I want to highlight as well. I'll do that at the end, after we have done the tracing. So now, how do we trace? Add.accept v over here. Right? Let's now go over that. Oh, sorry, just before that, it might be worth just to brush your mind. For the constant class, that's a base expression. And we got the accept method here. We simply say visit constant, and then pass the constant itself. And for the addition class, which is a composite expression, like a recursive case. And we still do a very similar line. And here we say v.visit addition. And then we pass this. And if you just one more thing to link back to the diagram. If you look at here, for each visit method over here that's defined in the visitor interface, you can see for constant, we're expecting a constant. For addition, we're expecting addition. That's why you see the this keyword over there to make it work. All right? All right. So that's about this part over here. And what about this part, the visitor? The interface we explain how many visit methods should be there depends on how many expression classes you actually have in order to visit. Here we got 3. Constant, addition, subtraction. And also, over here, we got visit constant. You can think about it's like a base case for the visit operation. And the visit addition is like a recursive case. And this was a diagram I drew last Thursday. Conceptually, we're going to trace in detail. Conceptually, if I have some expression E, which is addition, we got left subtree, and also we got right subtree. If we want to visit the entire tree, pretty much like we want to apply some recursive operation on the whole tree, what should we do? Well, basically, we want to recursively visit the left subtree, get the result. Also, recursively visit the right subtree, get the result, and put those results somehow together. That'll be the visit result for the entire tree. That's the idea. You'll do something very similar also for your projects if you chose the visitor option, not the action version. Okay, so now we are ready to talk about double dispatch. Let's now try to trace this method call. In order for us to trace this method call here, so we got add.accept. This accept method was defined at the top level expression class. So because of dynamic binding, we have to worry about which version of the accept is going to be called. Because accept can be the accept in the constant class, or it could be the accept in the addition class, or it can be many other possibilities. So now in this case, where should we go? Well, if you look at that, add dynamic type is addition. So that means that's so-called the first dispatch. Okay, I'm going to write it down here. The first dispatch is going to be dynamic type of add is addition. What does that mean? That means the version of accept in addition class will be invoked. Hope it makes sense up to now. Right, so dynamic type here is addition, so that means we're going to go for addition. And then when we go for addition here, we go for that accept. And once we go to the accept, the only line to trace is this line over here. All right? And there would be another instance of dynamic binding. Can anybody tell me what kind of dynamic binding is that for the second one? Please. Visitor, yes? Can you be more precise in this case?
Evaluator implementation.
Evaluator for the visitor edition. Exactly. Very good. Yeah. So guys, just to repeat what your colleague just said, which is completely correct. So here, the V over here is dynamically pointing to some evaluator. Oh, by the way, so this structure here is based on the previous page that we spoke about last Thursday. In case you forgot about the detail, you can refer to it. But the V here is evaluator, which is a dynamic type. So this will be the second dispatch. Second dispatch will be, and you can see we are passing the V over here. And the V dynamically is evaluator. Dynamic type of V is evaluator. That means the version of visit addition in evaluator is invoked, which is over here. And you might be wondering, well, you're only showing one version of visit addition. It seems that we have no choice. Actually, you do have choice. Let me just go back to the architecture diagram. If you look at the diagram here, at least for now, we got 1, 2, and 3 different descending classes for the visitor. Right? You can see visit addition here, version number 1, version number 2, and also version number 3. So you do have choices that you have to decide based on the dynamic type at the runtime. That's why there are 2 dispatches you have to make a decision on. Each one is so important. All right? All right, let's now move on. And now we're going to execute the visit addition here, visit addition. That's what we're going to do. And then I'm going to call this method over here. And then the this over here is really the context objects. And the this over here, since we were initially making this particular method call, add.accept v. So the this over here is really the add. Agree? So the addition here is really the ADD, which makes sense, just the top level. So that's our first visit. But things are going to be recursive. So let's see how it's going to work. And let's now trace this part here very quickly. It is so important. All right? But this is a simple case for us to consider. Idea would be we create 2 local variables, both of type evaluator. We got evaluator left, evaluator right. It's pretty self-explanatory. Evaluator left is going to be used to visit the left subtree. Evaluator right is going to be used to visit the right subtree, obviously. Right? Let's say we got these 2 evaluators, and then look at these 2 lines. That's kind of interesting. I'm going to highlight it. E dot left, E dot right. And then notice that we got accept again. And also we got evaluator also again. All right? Notice the following. We started with add.accept v. And then it boils down into e.getLeft or add.getLeft. Just add over here. Remember, e is simply just add. So get the left subtree over here, let it accept another evaluator, get its result. And then get the right subtree over here, let it accept another evaluator. And each visitor is supposed to store as part of their attribute or state the result. That is why you see in the architecture diagram, we actually got, for each one of them, typically you might just get some public accessor like a result. Of course, you can feel free to rename them if you want to and different types, right? We're only talking about just principle. And for each one of them, again, it's going to be another set of double dispatches. I'm going to do just one more, and then the other one will be exercise for you, all right? For this one here, it's going to be another double dispatch. For this one here, it's just going to be just another one. Every time you want to do some accept on some particular subtree, it's going to be another double dispatch, basically. And let's say for this one over here, we can now practice. Okay, anybody tell me, for this one here, what's going to be the first dispatch? Go ahead, please. What's the first one? Yes.
The constant implementation.
Yes, I agree. But just to be more precise over here, you can see for the first dispatch, I'm pretty sure that's what you meant, but I got to be more elaborate here. This is the context objects for accept. Its dynamic type is e.getLeft. Add.getLeft is simply constant. So that's the first dispatch because the dynamic type is constant. All right. So I'm just going to make a quick notes. This one over here has the dynamic type constant, which means we're going to go to the accept of version constant this time rather than addition. And for this accept over here, we're going to call this single line. Here comes the second dispatch. All right? That one should be quite obvious because it depends on what dynamic type it is for V. And V is evaluator left, which is dynamically a evaluator. So that means when we say v.visit constant here, we are actually going to call the evaluator version. And let's finish that. And if we go to the evaluator version of the visit constant here, that one there will just get the value of the constant itself because to evaluate a constant is the terminating case, just the value. So that means the evaluated left.result is going to get this result, which is 1. Evaluated right.result is actually eventually going to get 2. And then we're going to set a result for the overall evaluator, which will be 3. Right? You can see 1 plus 2, and then will be 3. The result, that will be the v dot result, 3. It's different layers. Guys, hopefully it's not too complicated. Let me summarize what you should know. Number 1, if I give you any example code, you ought to know what will be the first dispatch described in full detail, and what will be the second dispatch described in full detail. Especially when the tree structure itself is actually may not be this simple, right? Feel free to actually create yourself a little bit more sophisticated left subtree and try to use debugger in the Eclipse to see how the double dispatch is going to work. That'll be my suggestion for exercise in preparation for the exam. Okay? I'll write it down here and then to see if there's any further question. Okay, so here, exercise. Make more sophisticated left subtree and trace for double dispatch. All right, that'll be your exercise. Any question about the double dispatch? That's really the essence for visitor pattern. Right? All right, I presume everybody's okay? All right? Okay. The final points about visitor pattern is to revisit this, the design principle, because visitor itself is a design pattern. Being a pattern means it may be applicable in some scenario, but it may also be unpracticable in certain other scenarios. So we ought to know what they are. Okay? And we need an open-close principle to help us a little bit. Okay? So this part we have discussed them already. So that's the final slides. Okay? And let's now just go here. I'll show to you. I want to brush up your memory just about open-close principle very quickly, so you will be able to answer the question. So for the open-close principle, it tells you for your system, let's say in this particular example, we got two parts. Structure part for the syntax, the composite, and also we got operations, right? The different descendant classes for the visitor, right? Open-close principle tells you to follow as follows. Some part should be open, and some part should be closed. If you happen to choose, for example, let's say this part over here to be open, that means you are expecting more classes for the expression to be added over here. If you choose the other way, if you choose the operation itself to be open, that means you expect the structure over here to be rather stable. But this part here, you might just keep adding more operations to it. So there are two possibilities. And now we want to revisit these two possibilities and see which alternative would be suitable for visitor. See what I mean? Okay. Let's now take a look. Two more pages, and then we are done with the visitor. Let's take a look. Okay, so that's the visitor pattern architecture just there to help you think. Okay. Now, let me just guide you with a question. What if a new language structure is added? Obviously, if we want to add a new language structure, let's say currently we got addition, subtraction. Let's say we want to add multiplication, right? Let's say we want to do that. The fact that you want to add a new language structure, right? So that means you're assuming that the structure is actually open. And the operation part is actually going to be closed. And let's say if you do that. If I try to add a new class over here for multiplication. Let me do that first. All right, that's what it means. Are we okay so far? Just about adding a new construct, okay? Before I talk about the consequence, let me talk about the other alternative. Let's say we assume the structure part is closed, but the operation part is open. So that's why what if a new language operation is added? So here we are making different assumption. So we are saying that the operations is open. And the structure is actually closed. And in order for us to add a new operation, let's say right now we got evaluation, we got pretty printer, we got type checker. What about we got some code generation, for example? Maybe we want to generate assembly code. Okay? That means I'm going to add this class over here. Okay, let me just call that maybe assembly generator. Okay, like that. You can see in one case, we are adding a new language structure because that part is open. In the other case, we're adding a new operation because that part is open. Okay, now, can somebody tell me, as far as the single choice principle is concerned, which scenario is bad? Which scenario violates the single choice principle? That's the question. Once we answer that question there, we will know what will be the exact applicability condition for visitor pattern. William.
As long as now you need to add like 4 different
Okay.
methods.
Okay, good. Okay, that's very good. Awesome. Okay, that's exactly right. For this one here, think about the consequence. Remember the principle. As soon as we add a new language construct, we have to go to the visit. First of all, we go to the visit interface. We're going to say void visit multiplication, and then something over here. That's the header. Not only that, for every descendant class of the visitor, we have to implement accordingly. So there will be 1, 2, 3, and 4. 4 classes we have to touch to make the change. That apparently violates the single choice principle, which tells you there should be a minimum number of places you really want to modify. So that one violates. And I can tell you in general, if you got many operation classes over here, you got many places to update, of course, whenever you add a new language structure. Okay, so this one here violates single choice principle. This one tells you the following. Visitor pattern may not be good if your language structure over here is actually open. You may not want that. If it turns out your language structure is actually open, you may not want to use the visitor pattern. Because what would that correspond to in the Antler 4? That means you want to keep generating new skeleton code into your Antler 4 projects. On the other hand, you may just want to keep that as stable as possible once it's stabilized. And then only modify the model package, okay, for the operations. All right? So this will be unsuitable for the visitor pattern. And for completeness, let's now talk about the other scenario. Why would that scenario be okay to satisfy the single choice principle? Where would that be? Where would be the single place that we got to modify? Well, apparently, just that class, right? Would that be the only one, to be honest? Would that be it? Well, since there is no language structure to be added, so this one untouched. And we're only adding a new operation over here, right? And all we got to do, we are not even adding any visit method here because there's no new language construct. So all we got to do is create this operation class as a descendant class of the interface visitor, and then implement each of the visit method for the language construct. That's it, a single place. Okay? In this single place, implement all visit methods. That's it. So the single choice principle is satisfied. So if you go back to that slides, which I'm not going to read off the slides, and that would actually tell you, in order for the visitor pattern to be applicable for your projects, the language structure better be closed, but the operation better be open. Right? That's the really concluding remark for the pattern. Okay? And you can definitely go over everything has been discussed. All right. And there's a little bit digression, for our parsing lecture, but now we have covered composite and also visitor. You're definitely more than ready to do a large number of classes in your projects, for sure.